All right, good afternoon, and it's eighth period, and this is the last one of our little lead-in videos as we get ready to start creating our streakyhedrons. In this one, we're going to look at the actual time frame of what's going to happen when over the next several weeks as we go through this challenge. But first, we've been talking a lot about ideas and how some ideas, like you might think it's a bad idea, but it might not be. Well, here we're going to look at like things that just might happen accidentally, and a cool discovery comes out of it. Also, if you're presented with a constraint, how can you actually get around it?
Imagine you're asked to invent something new. It could be whatever you want, made from anything you choose, in any shape or size. That kind of creative freedom sounds so liberating, doesn't it? Or does it? If you're like most people, you'd probably be paralyzed by this task. Without more guidance, where would you even begin? As it turns out, boundless freedom isn't always helpful. In reality, any project is restricted by many factors, such as the cost, what materials you have at your disposal, and unbreakable laws of physics. These factors are called creative constraints, and they're the requirements and limitations we have to address in order to accomplish a goal. Creative constraints apply across professions to architects and artists, writers, engineers, and scientists. In many fields, constraints play a special role as drivers of discovery and invention. During the scientific process in particular, constraints are an essential part of experimental design. For instance, a scientist studying a new virus would consider, how can I use the tools and techniques at hand to create an experiment that tells me how this virus infects the body's cells? And what are the limits of my knowledge that prevent me from understanding this new viral pathway? In engineering, constraints have us apply our scientific discoveries to invent something new and useful. Take, for example, the landers Viking 1 and 2, which relied on thrusters to arrive safely on the surface of Mars. The problem? Those thrusters left foreign chemicals on the ground, contaminating soil samples. So, a new constraint was introduced. How can we land a probe on Mars without introducing chemicals from Earth? The next Pathfinder mission used an airbag system to allow the rover to bounce and roll to a halt without burning contaminating fuel. Years later, we wanted to send a much larger rover, Curiosity. However, it was too large for the airbag design, so another constraint was defined. How can we land a large rover while still keeping rocket fuel away from the Martian soil? In response, engineers had a wild idea. They'd design a sky crane. Similar to the claw machine at toy stores, it would lower the rover from high above the surface. With each invention, the engineers demonstrated an essential habit of scientific thinking, that solutions must recognize the limitations of current technology in order to advance it. Sometimes this progress is iterative, as in, how can I make a better parachute to land my rover? And sometimes it's innovative, like how to reach our goal when the best possible parachute isn't going to work. In both cases, the constraints guide decision-making to ensure we reach each objective. Here's another Mars problem yet to be solved. Say we want to send astronauts who will need water. They'd rely on a filtration system that keeps the water very clean and enables 100% recovery. Those are some pretty tough constraints, and we may not have the technology for it now. But in the process of trying to meet these objectives, we might discover other applications of any inventions that result. Building an innovative water filtration system could provide a solution for farmers working in drought-stricken regions, or a way to clean municipal water in polluted cities. In fact, many scientific advances have occurred when serendipitous failures in one field address the constraints of another. When scientist Alexander Fleming mistakenly contaminated a petri dish in the lab, it led to the discovery of the first antibiotic, penicillin. The same is true of synthetic dye, plastic, and gunpowder. All were created mistakenly, but went on to address the constraints of other problems. Understanding constraints guides scientific progress, and what's true in science is also true in many other fields. Constraints aren't the boundaries of creativity, but the foundation of it.
So just because there's a limitation on something, that limitation doesn't necessarily mean that you can't do it. It just means you have to find some new creative way to kind of, well, just do a workaround. You know, if as you're building your little forms here, like, well, you know what, the tape isn't working, or I don't like the way it looks, you know, it doesn't mean you stop. It means that you figure out a way around it. You know, they talked about breaking the laws of physics. You know, Einstein, when he did his theory of relativity, they're like, no, that breaks the laws of physics. But do you know what they did? They kind of rewrote the law. They rewrote Newton's second law to say, okay, this is good up to a point. After that point, Einstein, that's where he kicked in. So you never know what a mistake or a limitation is actually going to do for you in real life. So back to the timeline. So let's look to see kind of where are we. So right now, we're right here. It's Tuesday, the 23rd of February. We're in 8th period. Tomorrow is our whole school lightning day. And again, just like we've had lightning days earlier this year, this lightning day is dedicated to our STEAM challenge. You'll have the day to kind of just work and create and work at your own pace. You know, yeah, we're going to give you some waypoints so you don't get, you know, a little too sluggish. But we're going to structure the whole day for you so you get to work if you want, turn your camera on, send pictures of what you're doing to your teachers so we can put them online. Your teachers will be working with you also. You know, they're picking up the kids also. And just remember, just because you couldn't get one of these kits at the school doesn't mean you can't participate. In the instruction manual and what you heard earlier over these past couple of days tells you how to still compete and create in this challenge, but without having the kit. So once you build your streakyhedron, then over the next several weeks, in each one of your classes, your teachers are going to put on a lesson for you that's going to go with your streakyhedron. So once you've built it, don't take it apart. Just keep it and put it to the side. Your teachers will have more information for you about what those lessons will look like. Then when we're all done, you know, we can't go and like display them all in the library or in the auditorium. We're going to have a virtual exhibition, a virtual gallery. More details on that will follow as we get closer to it. Now, when we're all done with our streakyhedrons, don't take them apart. Whenever we come back in person, whenever that is, and as of right now, I don't know when it is, we're going to take all of our individual streakyhedrons and put them all together to make one giant uber streakyhedron in our auditorium lobby. So that's the end of all these 8 lead-in lessons. We hope you have a better understanding of what the project is and how you're going to do it, and just the whole process of creativity, STEAM, and innovation. So tomorrow at 7:45 for first period, start making your streakyhedron. And if you have any questions, just ask your teachers, because this is a project that all of us are working on together.